linear velocity and angular velocity, r omega. Then the relationship between angular acceleration and linear acceleration. Then we also learned that for one complete revolution, angular velocity is equal to 2 pi on t, and this is also equal to 2 pi times f. When you make t the subject, you can also say that the period is equal to 2 pi over omega. That is when you make t the subject from here. Then f is also equal to omega over 2 pi. These are very important relations we derived. Period itself, capital T, is given by total time divided by the number of complete revolutions. And frequency is also equal to number of complete revolutions divided by T. Because of this relationship, T is equal to 1 over F, or F is equal to 1 over T. These are the very important equations we have derived so far. Please, are we okay? Are we okay?
Yes, sir.
Okay. Now let's look at equations of circular motion or circular motion equation. Circular motion equations. Now, just as we have, when we look at uniformly accelerated motion, for linear motion, we have three main equations. Akusha, what's the first linear motion equation?
V is equal to U plus 80.
So we have V is equal to U plus 80. Isha, what's the second equation of motion? Isha, what's the second equation of motion?
V squared is equal to U squared plus 2A.
Actually, the second one is this. S is equal to UT plus half AT squared. The order actually does not matter. And the third one is what you called. Now V squared is equal to U squared plus 2AS. What is so important is knowing the three equations of motion. And they all work upon when the body is uniformly accelerated. Circular motion has similar equation. Circular motion has similar equations. For linear motion, we talk about velocity, linear velocity. But in circular motion, we talk about angular velocity. So whenever there is a talk about angular, then we are looking at either circular motion or rotational motion. Okay, so in circular motion, V would be omega. V in circular linear motion represents final velocity. And so here we'll talk about final angular velocity. Omega 2 is equal to U stands for initial velocity. Here we'll talk about initial angular velocity, omega 1, plus A is for linear acceleration. For angular acceleration, for circular motion, we'll talk about alpha. T is not different. So this is the first equation of circular motion. 2, the second equation, S in linear motion stands for linear displacement. In circular motion, linear displacement will change to what? Yes. Somebody to tell me. In circular motion, linear displacement will be called as
surface angular displacement.
Angular displacement. So S becomes theta is equal to initial velocity. So omega 1 times T plus half A alpha T squared. This is the second equation. For circular motion, this is the second equation. Then the third equation, omega 2 squared is equal to omega 1 squared plus 2 alpha theta. This is the third equation. So linear motion and then circular motion really have something in common. They have something in common. I'm coming, let me check. So give me 1 minute, I'm coming, okay? All right. I think she just sent me a message. So if we are to draw a table for the tree, this is what we actually have. Linear motion as against circular motion. For linear motion, that is to help you memorize easily. We have V is equal to U plus AT. And a circular motion, we have omega 2 is equal to omega 1 plus alpha t. For 2, the second equation, we have S is equal to UT plus half AT squared. In circular motion, we have theta is equal to omega 1t plus half alpha t squared. Let me change my marker. Then the third equation, we have equation 3, omega 2 squared is equal to omega 1 squared plus 2 alpha theta. Oh, sorry. We have v squared equals u squared plus 2as. For circular motion, we have omega 2 squared is equal to omega 1 squared plus 2 alpha theta. Then sometimes there is this equation which is obtained from average velocity. It's not a major equation. It's actually not a major equation. That is S equal to U plus V all on 2 times T. This is not a major equation because equation 2 and 3 are obtained from this. Okay, but we add it to the equations of motion as if it's a separate equation. So if we are deriving something, okay, for circular motion, then we have theta, angular displacement is equal to initial angular velocity plus final angular velocity, all divided by 2 times t. So these are the equations, linear and then circular. Now we use the equations to solve problems. When a question is given to you, okay, you look at the appropriate equation which goes with it, and then pick one of them to solving the problem. Okay. In linear motion, we often look at the terms like the body starts from rest. The body starts from rest. Agosia, when the body starts from rest, what does it mean?
It means initial velocity is equal to 0 meter per second.
So it means the initial velocity is equal to 0. Then when you are told that the body starts from rest, what does it mean? Comes to rest. Agosia, you answered it.
The final velocity is 0 meter per second.
Good. So the final velocity is 0. You find the same terms also used in circular motion. You find the same terms also used in circular motion. Okay. So look at the example I gave you yesterday. Look at the example. Okay, let me solve an example. The angular speed of a disk. I'm giving you the question. So the angular speed of a disk decreases uniformly the angular speed of a disk decreases uniformly from 12 radian per second to 4 radian per second. It decreases uniformly from 12 radian per second to 4 radian per second in 16 seconds. In 16 seconds. Calculate the angular acceleration and the number of complete revolutions made within the time. Calculate the angular acceleration and the number of complete revolutions made within the time. So within the time of 16 seconds, we have to calculate the angular acceleration and the number of complete revolutions. Can you try? Give it a try for about 2 minutes before we go through. So, is that we are told that it decreases uniformly from 12 to 4 radian per second. So, initial angular velocity is equal to 12 radian per second. Final angular velocity is equal to 4 radian per second within a time of 16 seconds. We are to calculate the angular acceleration. And then, now, when such a question is given, you see, because the angular acceleration, velocity or the angular speed is decreasing, we'll also have a decreasing angular acceleration. So you look at equation 1 and equation 1, 2, 3. Which of them will be appropriate, okay, for solving this problem? Yes. Which of the 3 equations will be appropriate to solve this problem?
The first equation.
So the first equation. So what is the first equation? Omega 2 is equal to omega 1 plus alpha t. And we are looking for alpha. Therefore, when we make alpha the subject, we have omega 2 minus omega 1 all divided by t. What is omega 2? Omega 2 is 4 minus 12 divided by 16. This is equal to negative 8 on 16, which is equal to 1 minus 1 on 2. And this is minus 0.5 radian per second squared. So if this had been linear motion, we'll term this as a deceleration. And this is also a deceleration because the angular velocity, angular acceleration is negative. Please, are we okay with the solution? Are we fine?
Yes, please.
The second question, we have to calculate the number of revolutions made in this time. Calculate the number of revolutions made within this time. What are we expected to look for here? What are we expected to calculate for here?
Please, the frequency.
The number of what? Revolutions. You see, frequency is number of revolutions per second. Per second. So the number of, look at something, is the angular displacement. Okay, now, Kenneth, what is happening is that if omega is equal to theta on t, and frequency is equal to n over t, if the time is equal to 1 second, then we'll say that the number of revolutions is equal to frequency. Are you okay? Are you okay?
Yes, sir.
If the time is 1 second, then we say the number of revolutions is equal to frequency. But look at something. When a body is in circular motion, if it covers theta, we are saying that this is the angular displacement. The angular displacement for one complete revolution is equal to what? What is the angular displacement for one complete revolution?
That is 360.
360 or 2 pi. Okay. So for when the body makes, hey, who is giving me feedback here? Please, if you haven't muted, mute yourself. Ella, mute yourself. Okay, so for number of, if it makes complete revolution, theta is 360. If it makes 2, theta is 720. If it makes 3, 10. So, do you get it? So, whenever we talk about number of, calculate the number of revolutions, it can also be the angular displacement. If n is equal to 1, angular displacement is 360. If n is equal to 2, angular. So when we calculate theta, we are also looking for the number of complete revolutions. Are you okay?
Yes,
Are you fine?
please.
So when we use equation, I think either 2 or 3, theta is equal to omega 1 t plus half alpha t squared. We can find this. We can find this. So let's determine theta. Theta, we have omega 1, 12 radian per second times the time 16 seconds plus half alpha is equal to negative 0.5 times 16 squared. So we have 12 times 16. What's 12 times 16?
190.
So the
It's
line is,
192.
come again.
192.
192. This is minus Okay, this is 16 squared divided by 4. Calculate 16 squared divided by 4 for me.
That is 64.
64.
Is it 64?
Yes, sir.
When you subtract 64 from 92, yes, subtract 64 from 92.
That is 128.
128 radian. Let's convert this to number of revolutions. Change angular displacement of 128 to revolutions. In fact, this is when you leave it in radian, it's correct. But the book has the answer in revolution. So let's change 128 to rev. So if 1 rev is to 6.28 radian, what will be 128 radian in revolutions? Do that for me. Yes, what have we had? What have we had for this change?
That is 20.382.
20 points. Yes, 382. So the answer is approximately 20.4.
38.
So the answer is approximately
Yes, sir.
20.4 rev. Let's do it for the understanding of those. So if you use ratio and proportion, okay, 1 over 6.28 is equal to unknown x over 128. Therefore, if you make x the subject, you have x is equal to 128 divided by 6.28. And when you do that, you have a value close to 20.4 rev. So the number of complete revolution, it means is for this to decelerate from 12 to 4, it means the disk must rotate almost 21 times. That's the number of complete revolution. It must turn and decelerate almost 21 times for its angular speed to change from 12 to 4. That is what it means. Please, any question? I'm giving you one to try. I'm giving you a question to try. I said when the question is given, you look at it and then decide the appropriate equation to use. All right, so a disc rotating, with angular velocity of 6 radian per second is acted on by a force for 10 seconds. is acted on by a force for 10 seconds, and the final velocity is, and the final angular velocity, of course, is 35 radian per second. And the final angular velocity is 35 radian per second. Calculate the angular acceleration A in radian per second, B in revolution per second. Calculate the angular acceleration A in radian per second and B in revolution per second. I think this must take you about 4 minutes to do this.
Please take your.
Hello?
Is the I, is it radian per second square or radian per second?
Oh, it's once the question is about angular acceleration, of course, it is radian per second squared, and I revolution per second squared. Okay. What did you get for the angular acceleration in radian per second squared? You had 2.9. Doma, what did you get to? Akuya is not here. Ella, Obenewa, what did you get? Obenewa. Aku, what did you get? Who is Aku? Akuya, are you the one? Janice, what did you get for the first part? Tati, what did you get?
Sir, please, I got 2.9 radian per second.
Kenneth, what did you get?
Please, for the I've got
The
2.9
first one.
2.9 radian per second squared.
Mami Araba, what did you get?
Yes, I had 2.9 radian per second.
Okay, so what about the second one? What did you get for the second question?
Please,
Mami
I
Araba.
had- Yes, please. Please, I
Mhm.
had 0.462 revolution per second.
0 what? 46.
2.
Okay, Akuya, Akusha, what did you get for the second question?
0.46 revolution per second.
30.
0.462 revolution per second squared.
Ghana, did you get the same? Ghana, did you get the same answer? Okay, so
Yes, sir.
let's see how to do that. Omega 1 is 6 radian per second. Omega 2 is 35 radian per second. T is equal to 10 seconds. Okay, so appropriately, equation 1 would help us. Alpha is equal to omega 2 omega 1 over t. This is an acceleration because the angular velocity is increasing. So 35 minus 6 over 10. And this is 29 on 10 equal to 2.9 radian per second squared. How do we change this to revolution per second? Alpha is 2.9 radian per 1 second squared. Meaning that we don't have problem with the denominator because it's already in second squared, but we have problem with the numerator. So we must convert. I'm coming. Quickly, we must convert the numerator to revolution, and that's all. Because the denominator is already in second squared. Okay, how do we do this? We know 1 rev equals or is to 6.28 radian. So if 1 rev is this, then x rev will be is to 2.9 radian per second. So if you can't use more divide blah blah, use ratio and proportion. 1 over 6.28 would be equal to x over 2.9 and make x the subject. If you make x the subject, you have x being equal to 2.9 divided by 6.28. And what is 29 divided by this? 29 divided by 6.28. Oh, quick one. Who is giving me the answer? Come again.
0.4.
0.46. 0.46. The rest of you, what are you doing? We are doing this thing
Yes,
together.
please.
Another way, please do not sit on the fence. If we are doing it, I expect each one of you to contribute to save time. Another way of doing the same thing is this. Convert omega 1, which is in radian per second, to revolution. And if 1 rev is to 6.28 radian. 6 rev. Will it be more or less? It will be less. If less, more divide. So this will be equal to 6 divided by 6.28 times 1 rev. And I think this will give her 1 point something. Calculate it for me. Do not waste time. 6 divided by 6. Sorry, it will be 0 point something. 6 divided by 6.28. What is it?
0.954.
954 rev. Then convert the other one, omega 2, which is 35 radian per second. So if 1 rev is to 6.28 radian, okay, you have 35 radian. What will be its equivalent in revolution? So if you don't understand, use ratio and proportion. 1 over 6.28 is equal to x over 35. So this must give us 35 over 6.28, which is equal to
5.570.
5.570. 57.
rev. So after converting each one into revolution, then alpha is equal to omega 1, which is 5.570 minus omega 1, which is 0.954 divided by the time. The time is 10 seconds. Subtract and divide by 10. Subtract and divide by 10. Alpha is equal to
0.46.
rev per second squared. So this is another way of doing the same thing. I'm giving you last question to try, then we move on to another thing. So get ready. A wheel revolving at 6.00 rev per second. A wheel revolving at 6.00 revolution per second has an angular acceleration of 4.00 radian per second squared. Has an angular acceleration a wheel revolving at 6.00 rev per second has an angular acceleration of 4.00 radian per second squared. Find the number of turns the wheel must make. Find the number of turns the wheel must make to reach 26.
Angular acceleration.
A wheel revolving at 6.00 revolution per second has an angular acceleration of 4.00 radian per second squared. Are we there? as 4.00 radian per second squared. Full stop. Find the number of turns the wheel must make to reach 26.0 revolution per second. Find the number of turns the wheel must make to reach 26.0 revolution per second and the time required. So the question is looking for the number of turns the wheel will make and then the time required to make this number of turns. Okay, enjoy your song. Correct, because Inshira, you didn't give me what you had. Inshira. Hey. Inshira, are you there? Okay. Okay, so the answers actually are 502 rev, and then the time is 31.4 seconds. Okay. Once you are getting it right, I think, let me test you for the last time with this question. Once you are getting it. So get ready and put this one two down. A car wheel, which is 30 centimeter in radius. A car wheel, which is 30 centimeter in radius, is turning at a rate of 8 revolution per second. 8 revolution per second. When 8 revolution per second, when the car begins to slow uniformly to rest. When the car begins to slow uniformly to rest in a time of 14 seconds. A car wheel 30 centimeter in radius is turning at a rate of 8.0 revolution per second when the car begins to slow uniformly to rest in a time of 14 seconds. Find the number of revolutions made by the wheel and the distance the car goes in the 14 seconds. Find the number of revolutions made by the wheel and the distance the car wheel, it should be the car wheel goes in the 14 seconds. I'm going over. A car wheel 30 centimeter in radius is turning at a rate of 8.0 revolution per second when the car begins to slow uniformly to rest in a time of 14 seconds. Find the number of revolutions made by the wheel and the distance the car wheel goes in a time of 14 seconds. So try this. Let's see what you can produce then. We continue our journey. I want you to leave the distance the wheel covers for me in kilometers. Leave the distance the wheel covers within the time in kilometer for me. Yes,
Sir, please, is the distance 336 joules?
no. So a car wheel 30 centimeter in radius. We are told the radius is 30 centimeter. It's turning at a rate of 8.0 rev per second. So omega 1 is 8.0 rev per second. When the car begins to slow uniformly to rest in 14 seconds. So the final angular velocity is 0 within a time of 14 seconds. We are to find the number of revolutions made by the wheel and the distance the wheel covered and the distance the wheel goes in a time of 14 seconds. Okay, so the number of revolutions will be theta. So if we use omega 2 is equal to omega 1 plus 2 alpha theta, can we get it? But that would mean that we get the value of alpha. Alpha is equal to omega 2 minus omega 1 over t. Omega 2 is 0 because the motion came to a stop. 8 divided by 14. So we have negative. What is 8 on 4? 8 on 4 is 4 on 7. What is 4 on 7? 4 on 7. 0 point what?
5714.
5714 rev per second squared. Because it was decreasing uniformly till it came to a stop. So the angular acceleration is negative. Okay. So if we are using this, then when we make 2 alpha, if we make theta the subject from this equation, because we are looking for the number of complete revolution, we have omega 2 squared minus omega 1 squared divided by 2 alpha. And so that must give us 0 minus omega 1 8.0 divided by 2 times negative minus 0.5714. Our answer must be positive because negative. Okay. So alpha theta is equal to, I'm coming. So we have 4 divided by, this will go into it, 4 divided by 0.5714. So what did we get for that?
Yeah, it's 8 squared.
8 point.
And then omega 1 squared.
Sorry. That's a squared. So 64. So 64, this is actually negative of 64 divided by 2. Okay, so that will be 32 divided by 0.5714. What's our final answer?
56.00.
56.00. Rev. Let me check what the answer is. Yes, 56 rev. So I think what you, Akuya, and Kenneth told me, you got this right. Now the distance in kilometer. What the distance, we are looking at this. And we've realized that the disc, the car wheel rotates 56 times. So if you are looking for the distance the wheel will cover, then using S is equal to R theta, we must get it. But let's change this to radian so that we'll have this in meter, then convert. 56 rev, if 1 rev is equal to 2 pi radian, then 56 will be this times 2 pi. 2 pi is 6.28. Okay, so when you multiply 56 by this, you are giving me theta in radian, SI units. So multiply 56 by 6.28.
Surface 351.94.
Well, come again.
351.94.
Mention the numbers. 6,
351.68.
351. This is radian. Then we change the radius into meter. Okay, the radius is this 30 centimeter. So this will be divided by 100. So this is 0.3 meter. So that S will be equal to 0.3 times 351.68. Whatever you get is in meter. But because the SI unit of linear displacement is meter. Yes, that is equal to
105.504.
105.04 meter. And let's change
Yes,
this
sir.
to kilometer. Let's change this to kilometer. Of course, you have to divide by 1,000, isn't it? So
0.
1, 2, 3. 0.11 kilometer. And that's the answer. Approximately 0.11 kilometer. That's the answer in the book. So we have 56 rev and 0.11 kilometer.
Mr. Dia.
Hello, Mr. Kuya.
Mr. Dia, so when you're finding the distance, can't you leave your Angular distance in.
In what? In rev.
Yes.
You see, you can, but if you leave it in rev, and then you come and substitute here, okay, because R is in centimeter, how to call it is the issue. So always work within SI units. SI unit. And I also did this because the answer is given. So we were working to the answers. The reason for my conversion to SI unit before we express it in kilometer. Because if the answer is there and you don't leave it in SI, you won't get the answer as presented in the book. Are you okay?
Yes, please.
If you have any question, ask. Ask. Okay, so the next thing we have to look at under circular motion is centripetal force. Centripetal force. I have a lot of these questions, so I'll send a lot of it on the platform. So you try, okay? I'll send the question and then the answers too, so that at least you work to the answers. Centripetal force. The word centripetal force it's a Greek word. Centripetal means center seeking. Means center seeking. So centripetal force is a center seeking force. A force which is always looking for the center of the circle. Okay. Kati, you learned centripetal force in JHS, isn't it? Kati,
Yes,
isn't it?
please.
What
Yes,
does it
please.
What does it mean? What is
It's a
centripetal
force.
force?
It's a force that helps and keeps the body moving in a circular path in motion.
Okay. The idea is that Mami Araba, what is centripetal force? Mami Araba. Akosia, what is centripetal force?
Yes, please.
What is centripetal force? Ah, yes, please. You think I'm looking for yes, please? Mami Araba, what is centripetal force?
Please, centripetal force is a force that attracts a moving body to its center or in a curved path.
Okay, the idea is there. But centripetal force is a force that keeps bodies in a circular path within the circle. The force is responsible for keeping bodies or objects that are moving within a circular path or moving in a circular path within the circle. Meaning that if such a force is not there, bodies cannot stay within the circular path. So once this is a circular path, then we expect a certain force which will always pull the body to the center. And once the body is there, once that force is there, the body would always stay within the circular path. So at every position of the body, we expect centripetal force to be acting on the body. I've indicated 4 positions of the body. There's the center O. Because if this is not there, the body moves away from the circular path. And then we say it skates away from the circular path, centripetal force. Okay. So it is a force responsible for keeping bodies moving in a circle within the circular path. The unfortunate thing about centripetal force is that it is not a force that seems to exist on its own, or it doesn't seem to exist because centripetal force is always provided by something else in the system. So examples of bodies in circular motion. Last time we talked about when an object is tied to a string and whirled. So an object tied to a string and whirled. So when you tie an object to a string and you whirl it, the object stays within a circular path. Over here, the centripetal force MV, okay, let me talk. Centripetal force that keeps the object within the circular path is provided by the tension within the string or tension in the string. And see over here, look at it. We have the centripetal force provided by the tension. So it is the tension that is producing the centripetal force, which I've indicated as Fc. Another example of circular motion, a car negotiating a bend or curve. So for a car to stay within a circular path, the centripetal force which keeps the car within a circular path is provided by, okay, let me give it in words. The centripetal force is provided by the frictional force between the road and the tires of the car. Another example of circular motion. S. The revolution of planets around the sun. This is another example of circular motion. Over here, the centripetal force which keeps the planets within the orbit. Okay, so the centripetal force in this case is provided by the gravitational pull or the gravitational force of attraction between the planets and the sun. Okay, and the last circular motion we'll talk about is 4. The electrons orbiting around the nucleus. The electrons in an atom, electrons orbiting around the nucleus. Here too, the centripetal force is provided by the electrostatic force of attraction, by the electrostatic force of attraction between the nucleus and the electrons. So it is always as if the issue is even that centripetal force in all situations is provided by something else. And so it looks as if centripetal force in itself doesn't exist. Within the system, it is always supplied by something else. That's the nature of the issue. It is always being supplied by something else within the same system. So if an athlete is running in an oval, the centripetal force which keeps the athlete within the oval is provided by the frictional force between the feet of the athlete and then the ground. That is the nature of it, centripetal force. Okay. In our next meeting, we'll look at what actually provides the centripetal force. Then we'll also look at why is its direction always towards the center of the circle. Then we'll look at how to calculate for centripetal force. What is the formula? Yes, I know some of you at least have the idea of a formula how to calculate for centripetal force. But how is it obtained? We'll look at all that in our next meeting. Okay, if you have any question, ask. Akuya, ask your question. Akuya.
Yeah.
I'll push you too. Ask your question.
Mr. Dio, please. Mr. Dio, please. A body moving along a curve will start from a point to another point.
Yes.
When it starts from a point, like it creates a radii, like
When
one
it starts-
radii, maybe from a it's to create a
Mhm.
radii, like maybe from point A to B.
Mhm.
So when it gets to B, it will also create another radii, which will give you two radii.
No, you see, for a circular motion, the radius is always fixed, constant. This is the center of the circle. Assuming a body starts from a point A, moves and then comes to a new point B. So long as the motion is circular, the radius from the position up to the center and then is the same. That is one characteristic of circular motion. Is that okay?
Yes, please.
So this radius is constant. That is how come the linear displacement, as we are saying, is equal to r theta. R is the constant of proportionality, and that refers to the radius of the circle. Agosia, what's your question? Any question? All right, if there is no question, I think this is why we draw the curtains on today's meeting. Okay. Good night to each one of you. Are you done writing what is on the board? I mean, all of you. Are you done? Okay. Bye-bye. Good night.